Welcome to today's Explainer. When we look at advanced robots today, whether they're navigating some crazy rocky terrain, putting together tiny electronics, or just dropping off a package on your porch, it honestly feels like magic, right? It really looks like they have a mind of their own. But behind that whole illusion of autonomy, there's this deeply fascinating, highly structured world of control systems. Okay, let's dive into this and demystify the mechanics of robotic control. We're going to break down exactly how machines use feedback loops to stay stable, hit their marks, and actually interact with the super unpredictable physical world around us. So, Section 1, the human feedback loop. Because surprise, you are the robot. To really get a grip on how a complex machine works, we actually need to look a little closer to home first. Before we even think about breaking down the mechanics of steel and silicon, we've got to look at our own biology. Our bodies use incredibly sophisticated control systems that engineers have spent literal decades trying to replicate. So, let's do a quick experiment right now. Seriously, if you're up for it, go ahead and close your eyes. Just shut them for a second. Okay, now take your index finger and slowly bring it up to touch the tip of your nose. How did you do that? How did your finger find that exact target without you seeing it? You didn't miss, you didn't poke yourself in the eye, and you definitely didn't need to visually guide your hand through the air. You just kind of did it.
Well, that's seamless spatial awareness, that is proprioception in action. It's basically the body's built-in ability to sense its own movement and position in space. Your muscles and joints are literally constantly firing off data back to your brain, tweaking your finger's trajectory in real time until, boom, it hits the target. This is, at its core, biological robot feedback. Your brain is just endlessly checking what your body is doing and correcting it on the fly.
Moving on to Section 2. The three-step correction, the mechanics of control. Now that we've seen how our internal biological feedback handles things, let's flip over to the mechanical side. Obviously, robots don't have muscles or a nervous system, but they use a remarkably similar concept to navigate. They rely on mechanical feedback loops to self-correct, and this brilliantly illustrates the core concept we call the feedback loop diagram. It all boils down to three fundamental steps. Step 1 is the set point. Think of this as the target goal, or the exact state the robot wants to be in. Step 2 is the error. This is where the system goes, uh-oh, and detects any deviation between where it is right now and where that set point says it should be. And finally, step 3 is action. The system steps in and applies a correction to wipe out that error. It is a continuous, never-ending cycle of command. Let's ground this with a highly practical example. Imagine you've got a simple robot, and it has just one job: drive in a perfectly straight line. That straight line, that's our set point. But as it's rolling along, maybe one wheel slips on a super smooth patch of floor, and the robot starts veering off course. Instantly, the robot's sensors pick up on that drift. That is our error. To fix it, the control system triggers an action, maybe slightly bumping up the speed of one motor to straighten the whole thing back out. It's just a constant, rapid-fire cycle. Set a goal, sense a mistake, fix it, over and over. All right, Section 3, open versus closed loops. The appliance test. Let's move to and see how this builds into the technology we're interacting with every single day. Because really, you don't need to visit a top-secret robotics lab to see these control systems in the wild. They're probably humming along right in your kitchen. But here's the catch. Not all machines use feedback. We really have to distinguish between two major types of systems here. So take a standard kitchen toaster. Is a toaster an open-loop system or a closed-loop system? Think about how it actually works. You pop the bread in, push the lever down, and a timer kicks off. But does the toaster actually know if the bread is toasted perfectly? Does it have any clue if your toast is turning into a burnt little brick? Nope, it doesn't. And that answer reveals a pretty stark contrast in how these systems are built. A toaster is a classic open-loop system. It literally just applies heat for a set amount of time. Zero self-correction. If the bread catches on fire and your kitchen is filling with smoke, the toaster doesn't care at all. It's totally blind to the outcome and will just keep glowing red until that timer pops. On the flip side, we have closed-loop systems. Think about your home thermostat. It actively monitors its own performance to fix errors. It doesn't just blast heat into a room blindly. It constantly checks the real-world results of its actions. Let's walk through a quick practice exercise to really lock this idea in. Look at the cause and effect chain of that closed-loop thermostat. First off, it reads the actual room temperature. Second, it compares that reading to your desired temperature, realizing, hey, it's gotten colder than the set point. Third, it takes action and kicks on the heat. And here's the beauty of it. Once the room hits that set point again, the error is gone, so it shuts the heat back off. Sense, compare,
act. It is constantly checking and responding. Which brings us to Section 4, Robots in the Real World, Scaling Up the Complexity. So we've got the basic math of a thermostat down. Now we're going to take that exact same closed-loop concept and scale it way up to advanced real-world robotics. Because here's the crazy part. The exact same foundational logic keeping your living room at a cozy 72 degrees is what allows multi-million-dollar machines to survive in super unpredictable environments. There's this fantastic real-life example from Brian Douglas. He points out how closed-loop control is the absolute magic ingredient keeping drones perfectly stable, even when they're getting hammered by high winds. Picture a drone just calmly hovering up in the sky. Out of nowhere, a violent gust of wind smacks it, pushing it hard to the left. If that drone was an open-loop system, it would just tumble out of the sky and crash. But because it's running a closed-loop control system, its sensors instantly detect that sudden error in its position and pitch. The motors counter-react in absolute milliseconds to fight the wind and stay perfectly locked in place. It is just breathtaking how vital this continuous feedback really is. So, if closed-loop feedback is the lifeline keeping a drone from crashing in a windstorm, why is this exact same constant feedback absolutely critical for a self-driving car trying to navigate a busy street? Think about the totally chaotic environment a car has to operate in, compared to that simple straight-line robot we talked about a few minutes ago. Well, it's all about reacting to the unknown. Autonomous vehicles require constant environmental monitoring to safely adjust their physical movements. A city road is just packed with unpredictable variables. A pedestrian suddenly stepping off the curb, the car in front slamming on its brakes, or hitting a random patch of black ice. Without a rapid, closed-loop feedback system continuously calculating set point, error, and action literally hundreds of times a second, a self-driving car just cannot react to those new obstacles. It would effectively be flying blind out there, just like our trusty open-loop toaster. And that brings us to our final section, Section 5, the illusion of intelligence, unmasking the machine. It's time for a little bit of myth-busting. You know, when we watch a self-driving car smoothly dodge a pedestrian or see a drone fight off a massive gust of wind, it's so incredibly easy to project human traits onto them. We naturally look at these amazing feats of engineering and call the machines smart or intelligent. But we really need to pull back the curtain here. So, the crucial point is this. Robots aren't actually smart, not at all. They don't possess consciousness or intuition or any true understanding of the world. What we perceive as intelligence is, in reality, just an incredibly fast, highly precise, mathematical illusion. It's literally nothing more than sophisticated cycles of sensing data and responding to it. The machine is just blindly following that feedback loop, detecting a deviation from its set point and applying a programmed action over and over and over again. I want to leave you with a final thought to ponder today. We now know that these machines rely entirely on the absolute precise timing of these mathematical loops. So what do you think would actually happen if a robot's feedback loop was tuned incorrectly? Like, how would a self-driving car or a hovering drone behave if its cycle of sensing and correcting was just a fraction of a second too slow? Or, on the flip side, what if it was too fast and it aggressively overcorrected every single tiny movement? It really makes you appreciate the incredibly fragile, finely tuned math that keeps our modern automated world running safely every single day. Thanks for hanging out with me for this explainer, and remember to keep questioning how the world around you actually works.